Today, we have our first lecture on hardware security. Now, what does that really mean? Again, we'll be looking at this from a broad perspective. Is hardware security all about cunning cryptographic contraptions to confound even the owner of a device from learning all of the computation happening on that device? Trusted or perhaps treacherous computing? Perhaps it's about the leakage of information that occurs in systems once you stop viewing them as being perfectly digital devices, which allows an attacker to measure information such as power to learn secrets, or perhaps even introduce faults with laser beams to see what you can leak once the system starts behaving improperly. The difference between the functionally correct and non-functional properties such as execution time is an ample source for information leakage. We'll take a look at the side channels that appear in cryptographic algorithms that allow key leakage via the time it takes to encrypt data, before looking at the more recent high-profile transient execution attacks, Spectre and Meltdown, which use similar strategies to leak secrets more generally on modern processors, which do lots of speculative execution that is invisible to the programmer, but all too visible to the attacker. Finally, we'll look at the opposite. How can you use hardware design modifications to help give security guarantees at high levels in this hardware-software stack by making it simpler or cheaper to eliminate programmer bugs such as buffer overflows? But first, common sense should tell us that if you really want to keep something secret, even from powerful network-connected attackers, isn't conniving cryptographic complexity. It's to lock the thing away in a box inaccessible to the outside world with a big padlock. That's still true even with high-tech systems, and locks, alarms and seals will play a part in most systems that we want to maintain real security properties on. In this first lecture, we'll look at the sort of attacks and defenses that often require physical access to the hardware, before looking at more general attacks and defenses in computer systems, hardware and architecture in the next lecture. Right, so walls and locks are inevitably, and often implicitly, a large part of any company's security infrastructure. Do you protect your infrastructure with thick concrete walls, or by making it as inconspicuous as possible, for example by placing it in the middle of a rack of another company's servers? And actually, even simple techniques like physical locks often have subtle weaknesses, in the same way that digital techniques and protocols do, that mean that we need to analyze them and their capabilities in the same way. Whether that's bumping on locks or denial of service on alarms, it's quite common that most of your defenses will be circumventable in some circumstances. Rather than making defenses truly impenetrable, the typical approach for designing entry controls and alarms is based on 5 stages: deter, detect, alarm, delay, and respond. You deter people from attacking in the first place by having thick walls or other challenging perimeter defenses such as complex locks. Then you have a detection layer of sensors and other barriers designed to create evidence, which is then fed into an alarm system to alert defenders of the system into action in enough time to prevent the damage. In order to help you with that, you then present further barriers to prevent the attacker from achieving their goal before your defense arrives, which is often less challenging than preventing them completely. Who do you want to be secure against? The capability of your attacker, your threat model, and the way you need to defend against them depends on what you need to protect. An example from Ross's book splits attackers into 4 example categories. So the first one we've got is Derek. Derek is a 19-year-old addict looking for his next fix. Derek will be more of an opportunistic criminal looking for simple, low-risk opportunities. Charlie is a 40-year-old with 7 convictions. Not necessarily intelligent, but very cunning and experienced, so knows the tools of the trade. He steals from shops and houses to find things to sell on to fences. Bruno, a gentleman criminal who steals art and takes pride in his work. Bruno is adept at lock and alarm hacking and is interested in getting into computer hacking too. And then we've got Abdurrahman, who heads a dozen agents with military training. He has access to specialist weapons and PhD-grade technical support, and is after top government targets. Indeed, he considers himself the good guy. So we've got this sort of sequence of unskilled to skilled to highly skilled potentially with help and to highly skilled with resources. Banks and computer rooms tend to be designed for Bruno. A lot of problems come about when you try to prevent the wrong threat actor of these. And a lot of it comes down to what you're actually trying to achieve. Is it deterrence or just redistribution of crime? Visible alarms can just redistribute crime to your neighbours, whereas invisible alarms that get criminals caught deter crimes for entire neighbourhoods. Environmental design matters as well. Communal spaces and visibility help because it means that things are overlooked so people are less likely to commit crimes. Single egress points, single points of exit, make criminals scared because there's a danger of them being trapped. And CCTV also helps to deter crime if there's a single exit that the CCTV covers. When you've got things like a safe, you might think that the safe full of money is the thing that you want to protect. But that's probably not always true. With safes, often, and with banks, the policy is actually typically to, if you have an attacker, give them all the cash they can see. Because it's actually the lives of the employees that are the valuable thing, and criminals will be able to exploit that knowledge otherwise. So often, safes are actually stored at the front of buildings rather than the back these days to limit the collateral damage. Don't focus on rare but exciting threats at the expense of mundane ones. If your walls are super secure but your roof isn't, is that really any good? Or will the criminals just adapt? Organisations such as NIST have tests and standards based on attacker capability, e.g. whether they're working just by hand or whether they've got power tools. But the organisations that certify locks, safes and vaults often make outdated assumptions. Their incentives may not really be aligned with yours very well, so the assumptions may be outdated or just unusual. And they can be a race to the bottom and thus lemon market within products of a given certified standard. So the ones that you'll be able to get will be the weakest ones within that grouping, because nothing else will remain available for sale by the market for lemons. So on to locks, which are a part of most security systems fundamentally. A typical example of a lock is the tumbler lock on screen, sometimes also known as a Yale lock. The correct key is the one which aligns all of the yellow pins so that it can be turned simultaneously. Most mechanical locks aren't actually that secure though, because they're vulnerable to bumping, which allows locks to be opened quickly and without damage by unskilled people. Bumping is far easier than lockpicking, which requires skill and specialist tools. Bumping just requires a specially made bump key for the type of lock without knowing the actual bitting of the key. So the way that works is like on screen. Your bump key is set at the lowest pin position for the key at all points, with a slightly rounded shoulder. Then you place the key under slight torsion and tap it with a rubber mallet. That makes the pins bounce, and the torsion makes them stick in position as the spring pushes them back down. With a few taps, you're in. So lockpicking doesn't require specialist skills anymore, and key manufacturers haven't kept up either, even in the commercial world. UL 437 and ANSI 156.30 are the standards in the area, and they specify resistance to picking and drilling, but not to bumping. So these days, it isn't just art dealer Bruno who can break locks. Charlie will be able to do so too. Another recent attack on locks are master key attacks. In many installations, as well as a key for each door, you also have a master key which can open all doors. The way that's implemented in pin tumbler locks is by having some extra cuts in the pin stacks. So we've got the red cut here and the blue cut too. My door key opens with a key pattern 223456, but also with the master key 334425, which I don't own because the master key opens all the doors, my key only opens mine. The issue is that you can search for the extra master cuts in the pin one at a time. I know my key 2, 2, 3, 4, 5, 6 works, so I then make a key with bits 1, 2, 3, 4, 5, 6. That doesn't work, so then I try 3, 2, 3, 4, 5, 6. That does, so I know the first master bit is 3. If I then keep going in sequence until I've found all master key bittings, I can save quite considerable time relative to a brute force search because it just becomes linear in the number of bits rather than more complex than that. So why don't we try a newfangled electronic lock system instead? Here you typically use cryptographic challenge response protocols to allow each keycard to enter rooms they're allowed to without revealing the key's secret to any snooping observers. But like with many real-world deployed crypto systems, these are hard to replace once deployed. And so since many such systems are old, they're vulnerable because of the constraints of Crypto War 1 in the 90s. MyFair Classic is one such example, which is still very widely deployed and quite easy to defeat. They deployed their own custom cryptographic algorithm with 48-bit keys to get export controls compared to at least 128 that you'd use these days with AES. Meaning the protocol is already on shaky territory. 2 to the 56 is not a particularly difficult brute force attack these days. Couple that with a weak random number generator and leakage of key stream material via error messages from devices, and these days many such installations have keys that are as easily copied as a metal key is. The moral? Be wary of companies that roll their own crypto. Anything less than AES or possibly triple DES, though that's also becoming increasingly deprecated, you should be quite concerned. And be wary of lock-in. If you've rolled out MyFair throughout your entire building, what's going to be the bigger cost? Replacing the entire building security system, or the perhaps remote possibility of a break-in by an experienced attacker? Well, it depends on the value of the thing that you're trying to protect. The other, perhaps more fundamental issue is a socio-technical one, holding doors open for strangers. You may make it policy that staff can't do this, but there's a compliance budget issue for breaking social norms. Your security may be less likely to be broken by the technology and more likely to be broken by users. Make sure you're protecting the right thing. You may need strategies where it's hard to break, such as turnstiles with high visibility to see offenders, but it depends on what your threat model is and how well overlooked your security is. So what's really protecting homes and business venues if it isn't the locks? Well, just like in network security, where you have intrusion detection systems to log as well as firewalls to block, if the burglar causes an alarm to sound or leaves an evidence trail, that may well deter them in the first place, or at least give you time to respond in the event something does go wrong. After all, why would a burglar try to break a lock if they could just smash a window? Well, the window smashing is significantly more visible and therefore significantly more risky. In your house, it's probably the car on the drive, the dog in the window, the visibility of the street, or perhaps your CCTV camera that's doing the heavy lifting on security, rather than your lock, for anyone more skilled than Derek the Addict. Let's say that we're an art gallery with a nice Picasso, and we've bought a lovely high-tech super optical cable that detects even the slightest movement of the aforementioned painting. Now let's imagine that Bruno hides inside the art gallery until the guards go home. He then steals the painting and the alarms go off as they should. Why should he care? He'll be long gone before any of the security arrive. Part of the issue here is integration. Your alarm should at the very least be integrated with your building's control system, but since these are often by two different manufacturers with their own lock-in attempts, this can be more trouble than it seems. Fundamentally, we can't get blinded by technology. Just because a solution is elaborate doesn't mean it will protect you against the right things. Don't get blinded by the Titanic effect. Is your security really unsinkable? And if it is, will that cause you to ignore the obvious threats? Then we've got, if we are trying to protect things via sensor, there are lots of different things that you can use to trigger your alarms. We've got vibration, switches, infrared heat, motion ultrasonics, microwaves, invisible barriers of microwave or infrared, pressure pads, video cameras, movement sensors such as cable ties or seismometers or even optical fibers, depending on how fancy you want to go. And the way that you use these is that for vibration detectors, you use those usually at the perimeter to detect things like fence disturbance, footprints, breaking of glass, or other attacks on the outside of a building. Switches, we put those on doors or windows. The door is open, the switch goes off, it sounds the alarm. If you're wanting to detect body heat, then you use passive infrared devices. You can measure the heat coming off them via an infrared camera. Motion detection you can do using ultrasonics or microwaves. You can have invisible barriers that also have microwave or infrared beams that when they're disturbed, you'll be able to sound an alarm. You can have pressure pads under the carpet, which in the most extreme cases may extend to instrumenting the entire floor with pressure transducers under every single tile. Video cameras nowadays often come with movement detectors and even face detectors to alarm automatically or provide a live video feed to a monitoring center that only needs to pay attention once the automatic detection has gone off. And then movement sensors on equipment like the painting we were talking about earlier. One of the big problems with all of these sensors, though, are false alarms. There are lots of things that can set off alarms, like ultrasonics or even air movement, and hardly anything will work and won't just go crazy in the presence of, say, lightning or hurricanes. At the perimeter, it's very hard to get a low false positive rate because of all of these effects. So that's why you focus on delaying rather than eliminating at the perimeter, because otherwise the noise to signal ratio gets too much. It's well known that a false alarm rate of around 15% degrades radar operators, and most security systems are well above that, so we can't be expecting our guards to be paying attention all the time. Denial of service is a real problem in all of these systems, and it can be a way for an attacker to circumvent them. If you keep just triggering an alarm till the guards stop listening, then the next time you trigger the alarm because you've actually broken in, no one will be paying attention. Police forces often no longer send squad cars to a venue after around 3 to 5 false alarms per year, so that's an easy way to mitigate the threat if you're an attacker. Video is a good line of defense. Video can be used as a secondary mechanism to confirm what's going on. The dispatcher can check first, and so police forces often prioritize alarms where there is a video feed as well to back it up, so that they don't have to keep going out to these false alarms. Again, a lot of this is about deter, detect, alarm, delay, respond. So you'll have things like fences and grass with sensor, and in a fence with infrared, and a big building to delay someone from getting to the really secret stuff, so your security can arrive in time. But there are real issues around feature interaction. Things like power cuts or other alarms going off, often if you've got a fire alarm going off, then there's probably going to be a lot of heat in the building. So that makes ignoring infrared sensors sensible. But it also means that you can no longer rely on your infrared sensors if there's a fire in the building. Attackers can exploit that. There was an example with in 2019 with Grüne Gewölbe, where €1 billion of treasures were stolen. And the complex feature interactions there was that there was a fire at a nearby building site to the museum, which damaged an electricity substation, which sent off the streetlights in the museum power. And so you go in and nick all of the stuff. And then there are other challenges around actually trusting what your alarms are telling you. So alarms are often designed so that they've got liveness signals, so that if someone just cuts the power to them, that will sound the alarm. But if someone can get control of that and spoof the signal, then you can't rely on it anymore. And there are usually two ways of trying to solve that. either you bury your cables in concrete and have multiple of them so that it's very difficult to get to at least all of them, or you use cryptography. In the cryptographic sense, you send a pseudo-random sequence or a challenge response and send the alarm if the response is not what you expected. But as with all cryptography, it's only good if the underlying protocols are decent, which they often aren't. Often you get short keys, bad random number generators, and as we've seen because of the first crypto war. And you can often replay the message more slowly if you want to have a little bit of downtime as an attacker. You just record the sequence over the time of a day and send it back just a slight bit more slowly, so that there's no outage, there's just a delay. So a 5-minute power cut while you go and nick something isn't going to be noticed. Another problem is that often the crypto key is the device number of the device, for example, which might be on the invoice of the thing that of the security system that you've bought, or on its box. And so there's a vulnerability in that the person you've bought the alarm system off of will know who the alarm system's gone to and perhaps what the key is. So the moral there is that if you're buying an alarm controller, buy it for cash. Don't buy it over any way that makes it very traceable back to your company, because you've got a threat that will be very difficult to mitigate otherwise. And that brings us to another example of a denial of service attack that you can do in this scenario, which is that you cut your rival's phone lines, wait for the police to come and go, and off you rob. In London, the insurance markets mandate that alarm controllers for premises of £20 million or more value have 2 independent means of communication to try and avoid this. At the moment, this will be perhaps one wired, one cellular, but what if those become just 2 separate 4G connections rather than the one wired, one wireless, which will be more economically efficient and simpler to install? Then you've got danger against certain types of attack, which may or may not be enough to break your security. And even if your network devices are buried in concrete, if your network connection runs through a curb box, then you're still screwed. You'll want 2 buried fibers to 2 different telephone companies and 2 different switch/router vendors. Big service firms have dozens of centers to try and make it harder to take out their security using a single attack on a single cable. Even smaller firms will want to have 2 or more. If you can't afford that sort of distribution, if you're not operating at cloud scale, you may want to ask yourself, who wants to dig? Who knows where to? And would you detect them in time? Now, who watches the watchmen? Bribery and corruption of your guards is always a major issue. Britain's biggest robbery in 2006 from the Securitas cash management depot involved robbers taking the manager and his family hostage, pretending to be police officers, and then compelling him to let them in and taking £53 million. Make sure that your security system protects all of the most valuable parts of the system, including the human actors, and add in controls to stop the human protectors of the system from going rogue, such as dual controls. Dual controls help for bribery in the sense that they will mean that you need to have 2 people go rogue instead of just the one for the attack to succeed. But they don't work as well for coercion. If you know that the other manager is being held hostage and their family will be killed if you don't give the code to release all of the money, are you really going to not release all of the money? One extreme case that can help clear your thoughts around whether your system is really secure or not is by thinking about if you were running a prison. How would I do this differently if half my staff were convicts on day release? And it's not just thieves that you're going to have to deal with and defend against. You're also going to have angry customers, spouses, and ex-employees where the threat might be an insider who knows an awful lot about your system. And if you're in a country where people own private firearms, then you might have to deal with shooters as well. So to summarize, on a physical security level, locks can be defeated, so alarms really do matter. Denial of service is really difficult to deal with and very important to deal with, because otherwise you'll lose the signal to the noise and your respondents will stop responding. You need to integrate detect, alarm, delay, and respond, in that your detection mechanisms need to successfully delay people enough to mean that you can respond properly, because it's going to be impossible to stop them from breaking into your system for the most part without that delaying mechanism. You need defense in depth. You have your security in these layers so that if one fails, the next one can step up to ease the burden. The perimeter is the least reliable and most important, because the perimeter will have lots of false alarms, but it's going to be the easiest way to keep people out. It's hard to keep guards alert under false alarms, so if you have too many of them and there's too much of a challenge to respond to them, then people will just stop listening. And so your attacker can just get round your system by denial of servicing the guards. Don't design for Charlie to keep out Bruno. If your attacker is going to be more sophisticated than someone who can bump a lock, then you need to have a security system to match, rather than assuming that a few padlocks will solve the problem. And you'll need to take advice on this. You'll need specialist subcontractors to implement a well-integrated security system, but you can't leave everything to them. Each one will be in their own vertical silo, and so you need to have specialists on your team. You need to have experts on your team who can integrate between all of these different subcontractors to get security systems that really communicate with each other and actually can implement detect, alarm, delay, and respond. So that's how you design for the protection of premises. But what if the devices you want to protect may actually end up in the hands of the attacker? For example, you sell an IoT device that stores your company's key material inside it, or a PIN terminal that you don't want leaking banking information, or even a pay TV card or SIM card, where there's temptation for the owner of the device to cheat or for forgery. In that scenario, you want tamper resistance. Either the system should break if someone tries to open it, or there should be obvious evidence of seals being broken, leaving an audit trail. It may be sufficient to make products tamper evident so that if someone dismantles a smart card and gets the keys out, they then can't reassemble it into something that will pass close examination. And if you have a product with security requirements, the threat models can often be quite subtle. It's not only whether a purchaser that can break it that matters. Often you have trust in the entire supply chain, which you will often seek to minimize. You need to know what you're trying to protect. Is it counterfeiting, alteration, duplication, simulation, diversion, dilution, substitution, or something else? And what do we mean by close inspection? Banking splits into three categories. Primary, by an untrained, inexperienced person who may have little to negative motivation. They might not care whether the banknote is a forgery, they might just want to have an easy life. Secondary, performed in the field by a competent and motivated person, such as a bank teller with limited equipment. And tertiary, with a full laboratory and with experts on hand. And the relevant standards in these cases are the FIPS 140 levels 1 to 4, with various different versions that have been updated over the years as attacks have grown more sophisticated, and the ISO standard 19790. A closely related field is security printing, which tries to distinguish genuine articles from forgeries. The most prominent example is banknotes. This includes techniques to accurately align front and back of the note, or simultan presses, which press them at the same time, as well as intaglio, letterpress, and embossing, which are different methods of creating raised or lowered portions of a document, Watermarks are another feature where translucent areas are inserted into the paper or polymer at manufacturing times, and other materials can be added at the same time, such as metal threads and holograms. Modern banknotes feature many different security features simultaneously, some designed for primary inspection, others for secondary, and others for tertiary. The idea is that by the time your forgers can easily reproduce evidence that can fool secondary or tertiary inspectors, your old notes will be revoked and new ones will be issued with new features issued. So, seals are a tamper indicating device to provide an evidence trail. For example, if products are interfered with in the supply chain. Think, for example, the heat sealing that happens on jars of jam, for example. Seals typically work by applying security printing to get a tag, then gluing this tag to the protected item or material to make it hard to remove, or to make it at least tear or deform if pulled from the object, like in the foil packaging of pills. Such seals are often quite easy to defeat. For example, secure envelopes, like the one I've got here, might tear and leave evidence if opened directly by having these security slits that you can see here. But if you heat treat them first and then iron the crumples out, you might leave very little primary or secondary inspection evidence. You can quite easily get into the envelope without tearing the security seals. Much of the goal is actually compliance rather than genuine security, or at least customary reassurance over genuine threat prevention. And if you're using seals, you may want a secondary mechanism to prevent failure if there is a real incentive to cheat. Equivalently, there are issues with random failure of seals for innocent purposes. Your system shouldn't break down in the face of such error. Defeating seals is often about defeating people, not defeating hardware. So if your inspection is meant to be performed by the public, or your seals are applied by those with little incentive to do so accurately, you may find them of fairly limited use outside of compliance and reassurance. Tamper evidence isn't enough if you'll never see the device again and if your attacker might be the device owner themselves. Then you need tamper resistance. There are a variety of devices that need tamper resistance for a variety of different reasons. It might be authentication in bank cards and phone sims, service control in train tickets and smart cards, trusted execution in laptops and phones, accessory control to stop your customers using third-party ink cartridges, or manufacturing control to stop your own supply chain from producing grey market versions of your own devices without paying you. A lot of the early work came from hardware security modules in banks. Rather than locking down the entire operating system of a machine, the secret parts go into a standalone cryptographic module, which is its own separate small computer that interfaces with the rest of the machine. These have a robust metal enclosure and contain equipment to perform encryption. The tamper-proofing is designed such that the RAM where the key is stored is zeroed whenever the object is opened, so a maintenance engineer replacing a battery can't get the keys. The idea is that after that, the HSM's owner can then reload the key material without it ever being exposed to any maintenance engineer. But real life is complicated. Why bother doing that when you can just tell the maintenance engineer the key for them to reload once they've caused the keys to be zeroed? That's far easier, isn't it? The moral being that elaborate security mechanisms only work with compliant users. Of course, there are ways to get into HSMs without actually opening the casing. Early devices were vulnerable to being cut through, for example. These days, you place the core of tamper-resistant devices in epoxy resin to make the core hard to physically attack, or at least leave evidence of the attack's occurrence. You can make it harder to extract the information in the first place by embedding things like tiny loops of wire in the epoxy, which are likely to get cut by any milling or etching and thus erase the key. But it's still often possible to expose the circuit without breaking the wires with sufficiently good lab techniques. Other problems come from systems not being as perfectly digital as you'd expect. SRAM, used for on-chip storage on computers, that has the same data in it for several years, ends up showing properties of what we call memory remnants. The key gets burnt into the SRAM bits, and so when the device is powered on, it just happens to assume most of the key bits rather than all zeros or random noise. You get similar effects with flash memory, even if it's been erased several times. In theory, SRAM is supposed to clear itself of any state when power is removed, but the reality is just more complex. At low temperatures, induced by freezing spray for example, data may persist for several seconds or even minutes, depending on the temperature. DRAM, used for computers' random access memory, that's the sort of off-chip bulk storage that you would consider to be random access memory, exhibits the effect to an even greater degree, allowing cold boot attacks to steal encryption keys from PCs and phones. More generally, side channels, or emissions that don't directly constitute part of the programmer's model but can leak secrets, are a real challenge for cryptographic devices. That brings us on to some of the more advanced attacks that can be performed on tamper-resistant devices such as smart cards to trick them into leaking their key. If you have an infrastructure where all of the smart cards you ship store the same key, as is often the case for TV decoders for example, then a single compromise is often enough to create real problems. In that case, your smart card may be shielded in various ways to prevent direct readout of its secrets, but it will have to draw power externally in order to perform its cryptographic functions. So, you can do forms of power analysis. The idea is that even if you can't directly read what a system is doing, if it consumes different amount of power depending on the input, you can use that to work out secrets. For example, let's say you're trying to guess a device password. Let's also assume that the password is too long and complicated to guess by brute force. Still, if we can guess it a byte at a time, and get a notification as to whether that byte is correct, it turns an exponential search into an easy linear one. That's why good systems are designed not to give away such partial answers, even on the time it takes to return an answer. Still, even if the time taken doesn't give the game away, it doesn't mean another side channel won't. Unless hardened against such an attack, the branching behavior that checks each element will give a different power trace based on whether it's right or wrong. So you change the first byte until you get a noticeably different power trace from all of the wrong answers, then move on to the next, and so on. In the example on screen, we see cycle 6 having a branch taken on top and not on the bottom trace. So we infer a bit of the secret and can keep repeating to learn the whole thing. Actually, cryptographic algorithms themselves can be particularly vulnerable to forms of differential power analysis. If the attacker knows or guesses the cipher implemented on a device, bearing in mind there are other good reasons to not roll your own crypto in any device that you make, then they can start correlating different power traces collected from operations with known either ciphertext or plaintext, either is fine, you don't need both, without knowing the exact implementation details, since it allows you to cancel out sources of noise. The differential part means that you cancel it out. This is true even if the algorithm is hardened against simple power analysis, by removing data-dependent control flow that gives away the secret. I.e. you can harden it against simple power analysis by doing that, but not differential, because if you have enough copies of the signal, you can overcome the noise enough to measure even very fine-grained power differences, caused by adding together different numbers using different amount of power, let alone taking different branches, for example. The basic idea of this trick is that you collect lots of traces of different ciphertext encryption traces and try to group them together based on which you think should feature the same computation on the same data based on your guess of a small bit of the key. If your guess is correct, then you'll get correlation and a notable spike, like the one in the example on screen, just over there, by comparing your two results. If your guess is wrong, you'll get no such spike, so you'll try a different value until you find the correct one, then move on to do the same with the next part of the key. If you want to do differential power analysis on DES, the data encryption standard, the way that works is that you try to guess the 6-bit subkey input of one of the 8 S boxes in the first round of the many rounds of DES. DES's substitution operations work by each S box taking in 6 bits of input and giving out 4 bits of output. So the S box gets 6 bits of plain text, or in future rounds bits from the previous round, XORed with 6 bits of the subkey, which in turn is 48 bits of the full 56-bit DES key, as the final 8 aren't used in the first round. What we want to do is work out whether our 6-bit guess is correct. From the guess of the subkey and the plaintext input, we can then infer the S box for each sample power trace with known plaintext input. So we take each of our plaintext power trace pairs from our various arbitrary sample inputs to the whole algorithm. We then take a single output bit of a single S box, call that B, take our current guess for the 6-bit key input to the S box, and split up our differential power traces into 2 groups. One where the guessed input B must have been a 0 with that key guess, and one where the output must have been a 1. If our guess is right, then we'll get a notable spike when we take the 2 sets as averages from each other. If not, then our guess is wrong, and we try again with the other 63 possible guesses of a 6-bit subkey. We then perform the same trick on 1 bit of each other S box to get another 6 bits of key until we get all 48 bits of the subkey. Then we finally brute force the 8 bits not used in the first round, the final 8 bits of the 56-bit key, to get us the full key. So that means that we split up our guesses of a 56-bit key with 2 to the power of 56 options to try, to 8 guesses with 2 to the 6 options, and 1 with 2 to the 8, which is far, far simpler. So, in summary, we have a set of known plaintext and power trace pairs, and that's it. Everything else is inferred based on a set of simple 6-bit key guesses and correlating the power traces. And you can do the same in reverse with just knowing ciphertext and power traces on the last round of DES rather than the first round of DES. So all you need is the plaintext power trace pairs or the ciphertext power trace pairs, and you've broken the algorithm. Though there are countermeasures available based around limiting the correlation between repeat runs, ultimately the attack generalizes to many devices that aren't as well protected as today's smart cards. In 2016, there was a demonstration of a work that could take over Philips Hue lamps by extracting the shared AES key used by every lamp to authenticate updates. There are other ways of exploiting physical properties of systems. In reality, devices aren't flawless digital computers. They're analog devices that give the impression of being perfectly digital through the switching of transistors. Real-world faults in that digital behavior, caused by voltage spikes or cosmic rays hitting transistors, and therefore causing incorrect bit flips not intended in the computation, changing a transistor from a 0 to a 1 or vice versa, are often assumed to be rare enough to not worry about, though the latest research on data centers shows that these sorts of incidental errors are actually enough of a concern to matter at scale. But we're interested in security of the device, where it's less random error that we're interested in and more deliberate circumvention. An attacker can deliberately induce the worst case behavior out of our supposedly digital devices. So what if your attacker can deliberately induce flips in transistors by shining laser beams at them, for example, or messing around with the clock frequency input to make the processor work out of its safe range and therefore glitch? They can, and it's a real problem for crypto algorithms which start to leak their secrets once they get their answers wrong via a technique called fault analysis. As an example, let's take a look at the public key cryptography algorithm RSA. If you're generating an RSA signature, S equals message to the power of D mod PQ, where in our diagram here N is PQ, N is the public key, which is P times Q, which are two secret prime numbers. The most efficient way to work this out is by working it out mod P and then mod Q, and then combining the two. But the problem is that if you get it right mod P but wrong mod Q, then the faulty computation leaks the secret. To show what I mean by that, we've got our example on screen of our signature, message to the power of D mod N, where D is our private key and N is our public key. And it's faster to calculate this by combining these two subsignatures, one of which is mod P and one of which is mod Q, where we've got our special functions of dP and dQ rather than d, which is a function of P and Q. That's all that means. And you combine these using the Chinese remainder theorem. What if we inject an error in the second one? So then we've got our new signature is the Chinese remainder theorem of one thing that is correct mod P and one thing that is wrong mod Q. So sig1, which is correct, and sig2 dash, which is not quite sig2, it's broken in some way. So when we've combined those to validate our message is equal to sig dash our broken signature power of E mod P, but it isn't equal to sig dash the power of E mod Q, where E is our public exponent. So it's right for one and wrong for the other. So that means that sig dash to the power of E minus message is divisible by P, but it's not divisible by Q. So P is just the greatest common divisor of our signature minus the original message and N the known public key, which is far easier to work out than the prime factor of N, which we otherwise need to do the prime factor of N to work out what our secret P and Q are, and thus break the security. This is far easier to do, and so you can also get out Q from it by just dividing N by P, which works out Q, and so you've broken the entire security of RSA. Now, that's as mathematical as I'm going to get in this course, but as well as how you have a simple power analysis and differential power analysis, you also have differential forms of fault analysis, which you can do on many different cryptography algorithms by comparing correctly executed operations to incorrectly executed versions. For example, if you can inject faulty bits towards the end of an AES cipher operation, you can work out how the fault bit propagates through an S box by observing which table elements get changed, and thus work out a part of the key. If you then work backwards doing more faults until you reach the start of the encryption, you can leak the entire key. So we've been through a lot of attacks, right from the simple tapping of a bump key to the mathematical complexity of fault analysis on RSA. But what is the moral that I want you to take from this? Well, if someone can benefit from subverting your system and can make an attack that can scale by breaking your devices, you need to pay attention to physical properties as well as digital. A lot of the standards are very wildly out of date, and manufacturers of security devices are often very misaligned. It's a lot more about theatre than real protection. So you need to work out for yourself what will really protect your system. And you need to know enough about these physical attacks to work out whether they're valid enough for your threat model, even if you don't understand the fine technical details, so that you can work out whether you need to pay more serious attention to them. Okay, so that's that story, and then next time, as I promised earlier, we're going to be looking more at the sorts of advanced side channels that you can do remotely, especially around microarchitecture and today's processors. The further reading for this lecture There are 3 different chapters in Ross's book, and I suggest that you go and look at all of them.